All right, so we're going to start looking at trig identities. Okay, we'll learn some basic identities, and we're going to even split those up over 2 days. All right. So first, I just want to talk about what it means if something is an identity. Okay? And I'll talk about it from kind of an algebra perspective first, and then we'll talk about what it means in trig. So suppose you have two functions, okay, in math, like f and g. Right, so you might have a formula in algebra like f of x equals something and g of x equals something. Okay, two functions. These functions are equal to each other if f of x equals g of x. Okay, what that means is if you plug a number into function f and you plug that same number into function g, you get the same answer every time. Okay, so an example of two functions that are equal, say f of x equals 3x plus 1, and g of x equals, let's say, 2 times x plus 1 plus x minus 1. Okay, if you simplify g of x, it will simplify to the same thing as f of x. Right? Do your distributive property, you get 2x plus another x is 3x. 2 times 1 is 2. Take away 1 is 1. So here's an example where f of x and g of x are the same thing. It's just not obvious because it's not simplified. Okay? And that's part of what we're going to see with trig identities. We're going to see two things that are really the same thing, like I'll just show you an example. Well, I'll show you one when we get to it. But you're going to see two things that look different, but they really are the same thing, okay? Like f of x and g of x. Okay, here's another example. If you already copied down the one I just did, you could just leave that. You don't need the second one. Okay, but there's two functions that are equal. They look a little different, but if you simplify one of them, it turns into the other. All right, so now we'll talk about the idea of what is an identity. Okay, so an identity is an equation that's true no matter what number you plug in for the letter. Okay, it's something that is always true. So in this case, I could write down f of x equals g of x, just like I did before, and that is an identity. No matter what you plug in for f, and no matter what you plug into function g, you're always going to get exactly the same number on both sides. So let's say you plug in, plug in 1. Okay, if I do that, Connor, what's 4 times 1? Plus 8? 12. So if I plug 1 in for x, I get 12 on the top. Skylar, if I plug 1 in for x here, what's 2 times 1? 2. Plus 4?
6.
And then times 2? 12. So I got the same thing. Right? So if I plug in 1, it's equal on both. If I plug in 2, 3, 4, whatever I plug in, you're always going to get the same value here and the same value here, as long as you plug in the same number for both x. Okay, so that's the idea of an identity. Okay, it's something that's always true, okay, no matter what number you plug in. Okay, so the first set of identities we're going to look at are called the reciprocal identities. And we already talked about these earlier in the year. Okay, the reciprocal identities are used, for example, if I said to you, do this on the calculator. Find the cotangent of 12 degrees. Do you have a button for cotangent on the calculator?
No.
No. You have a button for tangent. Okay, so what you have to do is take the tangent and flip it. Okay, that's the idea of the reciprocal identities. Okay, if you want to find the cosecant, you have to take the sine and flip it. And the reason this is an identity is because it works no matter what angle you want to use. I don't care if you want to find the cosecant of 5 degrees or negative 67.4. This is always the formula to do it. Always. Okay, so flipping the sine is the same as cosecant. Flipping the cosine is the same as secant. Flipping the tangent would give you the cotangent. Now, I could take that top one and rewrite it a little bit. What trig function could I flip that would give me sine, based on what I just wrote on the left? No, not yet. We're going to get to cosine a little bit. No, don't think inverse here. We're not going to use inverse. The cosecant. If you flip the sine and get the cosecant, then you can flip the cosecant and get the sine. You can flip them back and forth. Okay, how about cosine? What trig function could I flip and it would give me cosine? Yeah, the secant. If you flip the cosine, you get the secant. If you flip the secant, you get back the cosine. And what trig function could I flip that would give me tangent? Jake? Yeah, I could flip the cotangent. Now, there's really only 3 reciprocal identities up here. The 3 on the left and the 3 on the right, they're repeats. Okay? There's no difference between the top 2, the middle 2, and the bottom 2. All you did was take the one on the left and rearrange it a little bit to get the one on the right. Okay. So, any questions on those identities? So I'm not going to be able to write every single identity in every single possible way. Then there would be a lot. Okay, it's kind of like if I said, here's your formula for distance equals rate times time. Right? Or I could say you could write it this way. Well, that's the same thing. You just rearranged it a little bit. Okay? Or I could write it this way. Okay, so we're not going to take every single formula and write it every single way that you can. So what's on the left and what's on the right are exactly the same thing. Just like this and that are exactly the same thing. It's just rearranged. Okay, so those are our reciprocal identities. You flip one to get the other. Okay, and the other set of identities we're going to look at today are called the quotient identities. Okay, the first one I showed you yesterday. Sine over cosine equals tangent. Any guess what cotangent would be? You can write it the way I did up above. It's 1 over tangent. That's one way to do it. But how about in terms of a sine and a cosine? Cotangent is cosine over sine. Because remember, tangent and cotangent are reciprocals of each other. You flip one to get the other. Okay. Now, since I wrote theta here, what does that mean about what angles would this formula work for? Yeah, how do you know it would work for any angle? What on the board tells you this formula is always true?
Because reciprocal everywhere, then it should work. It should be it would follow the definition of identity.
Identity, yeah, that's what I was looking for. I wrote that these are identities, which means it doesn't matter what angle you use. It's always true. Yep, exactly. So you can also use the quotient and reciprocal identities with higher powers. So for example, suppose you had tangent squared equals, okay, instead of tangent equals. Anybody think they know what tangent squared would be? Yeah? Yeah, it would be sine squared over cosine squared. Okay, it's basically just squaring everything. Okay? Tangent cubed would be sine cubed over cosine cubed. We generally don't go that high. You might see it with squared. Technically, you could see it with any power you want, but in this class, I think that's probably as high as we could go. Now, let's look at cosecant. Okay. Cosecant is 1 over sine. So what do you think cosecant squared is? Yeah, it's 1 over sine squared. Cosecant cubed would be 1 over sine cubed. Cosecant to the 50th would be 1 over sine to the 50th. Again, we don't go much higher than 2. Okay? But I just wanted to mention that the quotient and the reciprocal identities can be used with higher powers. Okay. Any questions on those identities? Reciprocal and quotient. All right. So now, let's see if we can use those and try a problem. Okay. I want to simplify that. Okay, it says secant theta times cosine theta. Now, there's a simpler way to write that. Okay. Just like there is a simpler way to write that. Okay. To write that more simply, you use the distributive property. To write this in a simplified way, you're going to use the identities I just showed you. Okay. And a hint that helps a lot of the time, not all the time, is to take everything that you're given that's not a sine or a cosine and turn it into a sine or a cosine. If you look back at those identities, every single trig function can be written with just sines and cosines. You can write tangent as sine over cosine. You can write cotangent as cosine over sine. You can write secant as 1 over cosine. And you can write cosecant as 1 over sine. Okay, so everything in trig can be done with just sine and cosine. And usually what will happen when you write everything as sines and cosines is something cancels out. Okay? So we'll try that and see what happens. Okay, so using our identities from the other page, Jared, how can I rewrite secant with just using sines or cosines? Yeah, we're going to substitute in. Substitute that for that. Okay, so change secant to what it's equal to, 1 over cosine. Okay, so we have 1 over cosine times cosine. Now, cosine isn't a fraction, but if I wanted to make it a fraction, what could I put? Put it over 1. Now, when I multiply straight across, the same thing's going to happen as if you had something like this. If you can figure out the answer to this problem with numbers, you can figure out the answer to this one with words. It's exactly the same thing. So what happens when you multiply straight across here? What happens to the cosine? It cancels out. You have a cosine in the top and a cosine in the bottom. And as long as you're multiplying, they cancel out. And what are you left with for your final answer? 1. Now, when you do a trig identity, the answer doesn't always come out to a number. This one did because everything canceled out. Okay, we got a nice answer. What if I had addition? Okay, let me just do it with numbers first. 1/5 plus 5 over 1. Can I cancel the 5s? No. Okay, you can't do it with addition. The answer to this is 5 and a fifth. If you cancel the 5s, now the answer is just 1 on top and then a 1 on the bottom. It's just a 1. Okay? You can't cancel across a plus or a minus sign. Okay? But you can across multiplication. All right, let's try this one. Cotangent divided by cosecant. Do I have anything there that's a sine or a cosine right now? No. So I'm going to change everything. Now, you've got 2 ways you can write cotangent, if you go back and look at it. This is the first way. You can write cotangent as 1 over tangent. This is the second way. You can write it as cosine over sine. I can't say which way you should always use. Okay? It depends on the problem. And that's where this can get a little tricky. Okay? Some people like to just have the rule so they can do the same thing every single time. You can't do that here. Okay? You just have to try one of them and see what happens. If you start doing the problem and it's just getting worse and worse, you probably picked the wrong way to do it. Okay? I would go back and try the other way. Okay? So any thought about which way I could change cotangent? How could I rewrite that one? Yep.
Cosine over sine.
Yes. Let's write it as cosine over sine. Okay, so that's cotangent. And what about cosecant? Go back, look at your chart, because you can make a reference sheet, so you'll be able to look them up. Yep. I'd write it as 1 over sine. And now treat this problem just like it was numbers. Pretend you had something like 3/4 divided by 1/4. If you can solve that, this is going to be the same idea. So what do you do? Yeah, when you have a fraction over a fraction. You flip and you multiply. Okay. So you keep the top the same. And Jasenia, what do you get when you flip the bottom?
Get sine over 1.
Yep, you get sine over 1. And now when I multiply, what's going to happen?
Sines cancel.
The signs cancel. And what am I left with?
Cosine.
Just cosine. And that's my final answer. Okay? So if you wanted to take the cotangent of an angle and divide by the cosecant of the same angle, it's a lot simpler to just take the cosine and it's the same thing. Okay? So we're taking things that look kind of complicated and trying to make them simplified. Okay. Questions on that one? All right. Try that one on your own. Okay? See if you can simplify cosecant theta times tangent theta. Okay, and if you do it right, hopefully something is going to cancel out. All right, so let's take a look. So Connor, you were asking me, so what did you do with cosecant?
With cosecant, I changed it to sine over 1 Or 1 over sine.
Yep, 1 over sine. Okay, and Shakira, how about tangent?
I did sine over cosine.
Yep. Change that to sine over cosine. And now when you multiply those together, John, what happens? Think about if it was numbers, like 1 over 3 times 3 over 5. What would happen before you multiply those together?
Sines cancel.
Yeah, you could, as long as you got a multiplication sign or parentheses, you can cancel the same thing in the top and in the bottom. Okay, so now in the top, Dan, what are you left with?
1 over cosine.
Yep, 1 over cosine. And now, at this point, it's a reasonable question. Should you stop there, or should you go one more step? I would go one more step and make that not a fraction. So, Jesse, what's 1 over cosine the same as?
Secant.
Yep, secant. And that's the answer. Okay, so if you wanted to take the cosecant of an angle and multiply it by its tangent, it's a lot simpler to just take the secant in one step. Yeah.
Do you have to like change both of them to something? Because like there's like you want it to be sine cosine.
So far, we've changed everything to sines and cosines, yeah.
Okay, so you always want it to be sine cosine.
Not always.
Well, okay.
No. Only on the ones we've done so far. So there's different tricks we'll learn for different problems. This trick I call the changing to sine and cosine trick. All right. That trick works a lot of the time, but it doesn't work all of the time. Like in this problem. So how come changing everything to sines and cosines wouldn't work here? It already is sines and cosines, right? You don't have anything there other than numbers and cosines. So changing to sines and cosines won't help. But there's a second trick which will help. And that's to use the conjugate. Okay? We've seen the conjugate pop up at least once before. Okay? When we had a problem like this, complex numbers, and I wanted you to divide them, I said the trick was to multiply top and bottom by the conjugate, which would be 1 plus I in this case. You just change the sign of that thing in the middle. Well, we can try the same idea here. Okay, so look at what's in the bottom. It's 1 minus cosine. And what would be the conjugate of 1 minus cosine? 1 plus cosine. So let's try multiplying by the conjugate and see what happens. Okay, so multiply by 1 plus cosine in the top. And in the bottom. You know what? I'm just going to copy it. So I've got some space. Okay. Any questions on that first step?
It would be cosine squared over top? Or?
Nope, it's always the conjugate of what's just in the bottom. So the bottom is 1 minus cosine. You've got to put the same thing on the top and on the bottom here. It has to be the same thing. All right, so let's do it out and see what happens. For the top, I'm just going to leave it. I'm not going to distribute this out. Okay, the reason is because when you start multiplying these things together, you're going to get a cosine cubed. If we start getting things that are cubed, that's usually not the direction we want to go. All right? Generally, we're going to work with things that only have exponents of 2, not 3. So I'm just going to leave the top the way it is. 1 minus cosine squared times 1 plus cosine. Now the bottom, I want to do it out. And to do out the bottom, it's just like doing this. What property do you have to use when you want to multiply something with two sets of parentheses? Yeah, FOIL, or the distributive. Okay. So we'll start with, what's 1 times 1? 1. What's 1 times cosine? Just cosine. What's 1 times negative cosine? And that's going to work out nice in a second. And now let's do the last part in 2 steps. What's a negative times a positive? Negative. And what's cosine times cosine? Just like x times x is x squared, cosine times cosine is cosine squared. Now look at the bottoms. Anybody see something that's going to disappear? Yeah. Plus cosine, minus cosine. So now look at what you have left in the top. 1 minus cosine squared times 1 plus cosine. And what's left in the bottom? 1 minus cosine squared. So look at your fraction, and what you have right here is basically something like this. You have something times something divided by the same something. So what happens? Yeah, just like these would cancel out, these cancel out. And when you're done, all you're left with is 1 plus cosine. And that's your final answer. Okay, so we started with something that looked kind of tricky. 1 minus cosine squared divided by 1 minus cosine. And it actually simplified kind of nice. It's just 1 plus cosine. Okay, any questions on that one? Okay, I don't think with trig identities, the hard thing isn't necessarily doing the problem, it's knowing which method to use to do the problem. Should you change everything to sine and cosine? Should you try the conjugate? When you see enough problems, you start to kind of know. Unless you have fractions, you don't have conjugates. So example 2 would not be something you could even do a conjugate with. Neither is example 1. Okay. When I look at this one, the trick of changing to sines and cosines wouldn't work because everything already is. So you try to look at your problem and eliminate the methods that don't make sense and try the ones that do. And you're only going to have, like, I think 3 different tricks today. Change to sine and cosine, try the conjugate, and one other thing. Okay, try that one. And I'll give you a hint. This is very similar to the last one. So that's the approach I would take. And I would also avoid multiplying anything out in the top, because if you do, it's just going to be a mess. I'm going to hope that if I don't multiply what's in the top, something in the end just magically cancels everything out. Okay, so take a second, try it, and then we'll go over this one together. All right, so let's start to look at this one together. So this one, there's a couple things you could do. One, I see something here that's not a sine or a cosine. So I could go back to my identities and I could change this. Or the other thing I see is a fraction, and there's something in the bottom, 1 plus sine. Okay, so now I'm thinking, well, maybe I want to use the conjugate idea. And the answer here is you can do both. But what I would do is start with the conjugate. Because if you do that, something should cancel out. All right, so let's take and multiply top and bottom by the conjugate. What's the conjugate here? It's 1 minus sign. And 1 minus sign. Any questions on how Shakira got the conjugate? Now the top just looks like a mess to me. If I do all this out, it's going to be awful. So I'm not going to do it out because it looks awful. And I'm just going to hope that somehow something disappears. Right? Usually if it looks like it's going to be really bad, there's a way around it. At least in the problems I give you. So rewrite the whole top and leave it the same. Secant? 1 minus sine squared. 1 minus sine. Now, do out what's in the bottom, and I think you'll see something cancel. Okay, what's 1 times 1? You get 1. What's 1 times negative sign? And then 1 times positive sign? So I don't need to write that. Whenever you multiply conjugates, don't worry about the outer and the inner. They're just going to cancel. And then what's positive times a negative? Negative. And what's sine times sine? Sine squared. So now what cancels out there? That 1 minus sine squared. And now all I'm left with is secant times 1 minus sine. It's fine to stop there. Okay, so it looked like it could have been pretty bad, but really it was just that one step, multiplied by the conjugate, and then it just canceled something out. Okay, any questions on that one? All right, so the last type. Any thoughts what I could do? I'm going to do that one, and that one's going to be the same process. What do I have written here? I have two different what? Think of it more like what these things are called. I have two different fractions, and if I want to add fractions together, what do I have to have? I have to have the same denominator. So if I had something like that, well, actually now I'm going to bring up something else. Could I cancel the 3's here? No. Not with addition. Okay, with addition you can. If it was multiplication, you could. Okay, but that's not what I was going to get at. If I want to get a common denominator, what's the common denominator between 4 and 3? 12. Okay, so to get the common denominator, you take the denominator that you have, take the 3, and you multiply the other fraction by that denominator. Okay, that'll turn it into a 12. Now, on the fraction on the right, take the denominator that you had, which was a 4, and multiply top and bottom, and now you've got a common denominator of 12. Any questions on what I did right there? That's just basic adding fractions. Okay, let's try the same thing right here. What would my common denominator be? It's not a number. What is it? Cosine times cotangent. The common denominator is the product of the two that you have. Like in this case, it was a 4 and a 3, and everybody said 12. Well, here it's a cosine and a cotangent. So the common denominator is cosine times cotangent. Now, if that was a number like 4 times 3, I would multiply it together and write something. I can't. That's all I can do. What is the denominator on the left missing to make it have the common denominator? It's missing the other denominator. So multiply top and bottom by the other denominator. Cotangent. And what is the denominator on the right missing? It's missing cosine. So multiply top and bottom by the other denominator. Okay. Cosine. Cosine and cosine. And I'm going to hope that somehow that makes something good happen. Okay, we'll see. Okay, so now I have cotangent times sine, which we've had little problems like this earlier, so maybe I can do something with that. And what else do I have? Plus, it's just 1 times cosine. All right. What could I do with this part? Yeah, watch what happens if you change cotangent to cosine over sine. You get cosine over sine times sine. Okay, and everything else we could just keep the same. Why did I start changing to theta? It doesn't matter what letter you use, but just use the same letter all the time. If you use x, that's fine. If you use theta, that's fine. If you use y, just keep it the same throughout the problem. So cosine x times the cotangent of x. What cancels out there? Yeah. Sine, sine. Sine in the bottom, sine in the top. What's left in the top now? Cosine plus cosine. So how many cosines is that? 2. So 2 cosine x in the top, and what's left in the bottom? Cotangent of x. Now look closely. Is there anything else that the top and bottom have in common? Another cosine. Now, the way I'm writing this out, I'm taking up a lot of space because I'm showing you every single step. There's a lot of things I could be canceling out in my head as I go, but if I do that, I think it's going to be very confusing. So that's why I'm showing every single step. Okay, so that's gone. And that's a pretty simplified answer. Okay, if you weren't sure if you should do more with this, you could come ask me on the test. But that's a good stopping point for that problem. Yep, did I make a mistake?
So you don't touch
The
the 2
2?
attached to the cosine?
Nope, just like if you had, let's say, 2 times 5 divided by 5 times 7. That's exactly the same setup as this. You cancel the 5's, but you don't touch the 2. You leave this, and you leave that. Just like I left this, and I left that. Okay, other, yeah?
You also simplify that to tangent x?
You could do some more with this, but I'm not going to. Yeah, that's a good. If you understand how I got to this point, I'm happy. Okay. Any other question on that? But you are correct.
So I did it in 1 or 2 steps.
Yes, there might be even shorter ways to do it. This is an identity where it's kind of like driving from here to Worcester. It's not super complicated, but there might be a few different ways you could do it. Okay. right, and let's write this one. This time I'm giving you the same trick. Write with a common denominator. So now I'm starting to think in my head, if I didn't write down this trick till example 5, there might have been a simpler way. There was a lot simpler way to do example 4. But that's okay. You know, sometimes you figure out a simpler way after you do it. And I didn't see it at first, but now I do. Real quick, I want to look at example 4. What's sine over cosine the same as? Sine over cosine is the same as tangent. And what's 1 over cotangent the same as? That's also tangent. And what's tangent plus tangent? 2 tangent x. So there was actually a much simpler way. This wasn't wrong. Everything we did here was right. But it was like the least efficient way to do it. But a lot of times when you do problems on your own, that's what's going to happen. You're going to do it that way, and you're not going to see the quick way to do it. So it happens to me too. All right. Now, example 5, there is no quick trick here like I just showed you. You have to do it with a common denominator. Okay, so what's the common denominator going to be? Sine times cosine. What's the first denominator missing? Cosine. And if you do it on the bottom, you got to do it on the top. What's the second denominator missing? Sine. And if you do it on the bottom, you have to do it on the top. Okay, and looks like it's going to be kind of messy, but there's actually quite a big part of it that's just going to disappear. Okay. What's cosine times 1? Cosine. What's cosine times sine? Don't think too hard about it. Just cosine times sine. Yeah. And you might look at it and say, well, why did he do that out? And it's because I'm seeing a negative cosine sign here, and I see a positive cosine sign here. So I'm just seeing if I do it out, something's going to disappear. Now, do this one out. What's sine times cotangent? Just leave it as sine times cotangent. And now this is the part I want you to notice. What's negative cosine times sine? Negative cosine times sine. And the bottom is just cosine times sine. Now look at the top. Does anybody see something that disappears there? What disappears? Positive cosine sine, negative cosine sine. Whenever you have two things, one's positive and one's negative, they disappear. Right? So now let's copy what's left. Cosine plus sine times cotangent over cosine times sine. Now, I'm looking at that because it has something in it that's not a sine or a cosine. Cotangent. What can you change cotangent to? Keep everything else the same. So I just copied down everything except the cotangent. What did you say it was? Cotangent is cosine over sine.
So then the signs cancel.
And then that also cancels that out. And what are you left with in the top now?
Do cosine over.
Yep. Cosine plus cosine. That's 2 cosine. Be careful when you're doing like cosine plus cosine versus cosine times cosine. Okay. Cosine plus cosine is 2 cosine. What's in the bottom? Cosine times sine. Anything else that cancels? Cosines. And what are you left with? 2 over sine. Okay, that one is, that's more of like that's a hard one. Okay, that's as hard as we get. Okay, so when you're doing the homework, don't get discouraged if you get stuck. You're going to get stuck on them. Okay, some are going to be really quick and simple. Some of them are going to be harder. So just keep in mind we're going to practice this again tomorrow, and then we'll practice it again on Thursday. And we'll review again on Friday before the test. Okay, so homework tonight, I'm going to give you, it's a worksheet. And I'll put the worksheet in the video too.